Curves in industrial design, barycentric combinations. Given a line segment joining 2 points A and B, it's easy to find its midpoint, the point halfway between A and B. We can write the point M as half A plus half B. And we can represent any other point on the line segment AB in a similar way. If we move P, the representation of P in terms of A and B changes. We write alpha for the coefficient of A and beta for the coefficient of B. Alpha and beta sum to 1. And they express the ratio into which P divides the segment between A and B. We think of alpha as the contribution of A to the position of P, and beta as the contribution of B to the position of P. When alpha decreases, beta increases, reflecting that B contributes more to the position of P. As beta increases towards 1, P moves to B, so that when beta is equal to 1 and alpha is 0, we're at B. On the other hand, when alpha is large and beta is small, we get closer and closer to A, so that when alpha is 1 and beta is 0, we're at A. Any point on the line segment between A and B has the form alpha A plus beta B, where alpha and beta sum to 1 and are non-negative. We say that P is a barycentric combination of A and B. If alpha is bigger than a half, so that beta is necessarily less than a half, then P is closer to A than it is to B. If alpha is less than a half, so that beta is greater than a half, then P is farther from A than it is from B. The points inside a triangle can be described in a similar way. We sweep the triangle out with the line segments that join one of its vertices, here C, to the points on the side opposite that vertex, here the side joining A to B. For instance, here we see the point Q in the triangle. First, we regard Q as lying on the line segment which joins C to the point P on the opposite side, and we can write Q as a barycentric combination of C and P. P lies on the line segment that joins A to B, so we can write P as a barycentric combination of A and B. When we substitute the expression for P as a barycentric combination of A and B into the expression of Q as a barycentric combination of P and C, we obtain an expression for Q as a combination of A, B, and C. A particularly interesting point in the triangle is its barycenter, defined to be 1/3 A plus 1/3 B plus 1/3 C. This is something like the midpoint of a line segment, which was 1/2 A plus 1/2 B for the line segment joining A to B. We can think of the barycenter as an average of the 3 points that are the vertices of the triangle. It's somehow the center of the triangle. Any point in a triangle with vertices A, B, and C can be written as a combination alpha A plus beta B plus gamma C, with alpha, beta, and gamma summing to 1 and non-negative. And we say that P is a barycentric combination of A, B, and C. The relative values of alpha, beta, and gamma describe the relative position of the point with respect to the vertices. So for instance, if alpha is bigger than beta, then the point is closer to A than it is to B. If beta is bigger than gamma, then the point is closer to B than it is to C. If alpha is bigger than gamma, then the point is closer to A than it is to C. There are various different relative relations between alpha, beta, and gamma, which divide the triangle into different regions, corresponding to whether the point is closer to A, to B, to C, and so forth. For instance, the region where alpha is bigger than beta is bigger than gamma corresponds to a point which is closer to A. It's closer to B than it is to C, but it's closer to A than it is to anything. In general, we say a point P is a barycentric combination of the points A1, A2 to AN, if P is written as a linear combination, alpha 1, A1 plus alpha 2, A2, and so forth, with coefficients that sum to 1 and are non-negative. It's important to note that the point need not lie inside the polygon with vertices A1, A2, A3, and so forth. Although this was the case for line segments and triangles, it need not be the case as soon as we have 4 or more points. Here we see a point P, which is a barycentric combination of A1 and a point Q, which lies on the line segment joining A4 to A3, but lies outside the polygon formed by the 5 vertices. In order to remedy this problem, we introduce the following notion. The convex hull of a polygon is the smallest set that contains any line segment joining 2 points in the polygon. Here we see 2 red points lying in the polygon formed by the 5 vertices, and a line segment joining them, which lies partly outside the polygon. It does, however, lie inside the convex hull of these vertices. Any point that's a barycentric combination of a set of vertices, even though it lies outside the polygon formed by those vertices, necessarily lies inside the convex hull of the polygon with those vertices. When we refer to 4 or more points, there are many ways to express a given point in the plane as a barycentric combination of these points. Here we see 4 points that determine a rectangle, and we see their center, indicated by O in red. We can write it as a barycentric combination of A1 and A3, or of A2 and A4, or the segment which divides the region horizontally, and one can imagine there are other ways to write O as a barycentric combination of the 4 vertices. To summarize, the points on the line segment joining A and B can be written as alpha A plus beta B, where alpha and beta sum to 1 and are both non-negative. Every point in the triangle with vertices A, B, and C can be written as alpha A plus beta B plus gamma C, with alpha, beta, and gamma summing to 1 and non-negative. And more generally, any point in the convex hull of a polygon with vertices A1 to AN can be written as a linear combination of those vertices, with coefficients that sum to 1 and are non-negative.